Welcome to this comprehensive guide on essential research methodologies that every researcher must master. Research methodologies form the backbone of scientific inquiry, providing systematic approaches to discovering new knowledge and validating existing theories. Let's start by understanding what we mean by research methodology and why it matters. A research methodology is a systematic plan for conducting research and answering questions in a rigorous and reproducible way. It provides a framework for collecting data, analyzing results, and interpreting findings with scientific validity. Research flows from question through method to answer, with methodology ensuring this process is rigorous and reliable. You might ask, why do we need different methodologies? Why not just one approach? The answer is that different research questions require different approaches, just as different tools are needed for different jobs. Let's explore quantitative research methods, which focus on numerical data and statistical analysis. Quantitative research deals with numbers, measurements, and statistical analysis to test hypotheses objectively. Quantitative methods use data points to identify patterns and relationships, like this scatter plot showing a linear correlation. A key technique in quantitative research is statistical hypothesis testing, which helps us determine if our findings are significant or just due to chance. We start with a null hypothesis, such as H0, stating that two population means are equal. Against this, we test an alternative hypothesis H1, stating the means are different. If our p-value is less than 0.05, we reject the null hypothesis with 95% confidence. For example, testing a new drug's effectiveness requires quantitative methods to compare treatment and control groups. We might have 100 patients in a treatment group and 100 in a control group, measuring outcomes numerically. Sample size calculation is critical in quantitative research to ensure adequate statistical power. The sample size formula accounts for significance level alpha, power beta, variance sigma squared, and expected effect size. The pooled standard deviation combines variance from both groups weighted by sample size. Let's do a numerical estimation. If our expected effect size is 0.5 standard deviations, we need approximately 64 participants per group, so 128 total participants. Now let's explore qualitative research methods, which focus on understanding experiences and meanings. Qualitative research focuses on understanding human experiences, meanings, and the context in which they occur. It uses techniques like interviews, observations, and textual analysis to gather rich, detailed data. Qualitative research follows a cycle of interviewing, observing, analyzing, and interpreting data iteratively. For example, understanding patient experiences with chronic illness requires qualitative methods to capture the lived reality. You might wonder, how many participants do we need for qualitative research? The answer is that we continue until we reach theoretical saturation, where new interviews add no new themes. Typically, saturation occurs around 12 to 20 participants, though this varies by research context. A key concept in qualitative research is thematic analysis, where we identify patterns across the data. Thematic analysis moves from raw data through codes and themes to develop theoretical understanding. Mixed methods research combines quantitative and qualitative approaches for comprehensive understanding. Mixed methods combines the statistical power of quantitative research with the depth of qualitative insights. Mixed methods creates a third space where quantitative and qualitative approaches complement each other. There are three main mixed methods designs: sequential, concurrent, and transformative. Sequential designs conduct one phase first, then use those results to inform the second phase. For example, we might conduct a survey first, then interview participants to explain the quantitative findings. The key is integration, where we combine both data types to produce insights neither could achieve alone. Experimental design is essential for establishing causal relationships between variables. Experimental design is the gold standard for establishing causality because it controls confounding variables. Key features include random assignment, a control group, and manipulation of the independent variable. Random assignment ensures groups are equivalent at baseline, isolating the effect of our intervention. Effect size, measured by Cohen's d, quantifies the standardized difference between groups. Cohen's d equals the difference in means divided by the pooled standard deviation. The pooled standard deviation combines variance from both groups weighted by sample size. By convention, d equals 0.2 is small, 0.5 is medium, and 0.8 is large effect size. Let's work through a numerical example. Say treatment group mean is 75, control is 65. If pooled standard deviation is 15, then d equals 10 divided by 15, which equals 0.67, a medium to large effect. When experiments aren't possible, observational studies provide crucial insights. Observational studies are used when experimentation would be unethical or impractical. Main types include cross-sectional snapshots, longitudinal tracking over time, and case control comparisons. Longitudinal studies follow participants over time, measuring outcomes at multiple points. The main challenge is confounding variables that might explain observed associations. In case control studies, we calculate odds ratios as A over B divided by C over D, which simplifies to AD over BC. What does an odds ratio of 2.5 actually mean in practical terms? It means the exposed group has 2.5 times higher odds of the outcome compared to the unexposed group. Think of it like betting odds at a casino. One group has much better odds than the other. Survey research is essential for gathering data from large populations efficiently. Surveys enable systematic data collection from large samples, providing population-level insights. Key considerations include proper sampling, careful question design, and achieving adequate response rates. We draw a representative sample from the larger population to make inferences about everyone. The sampling error formula tells us how precise our estimates are. Standard error equals population standard deviation divided by square root of sample size. We construct confidence intervals to quantify uncertainty in our estimates. The 95% confidence interval is the sample mean plus or minus 1.96 times the standard error. For example, if mean satisfaction is 7.5 out of 10, with standard error 0.3, the 95% confidence interval ranges from 6.91 to 8.09. Response rate matters greatly. We should aim for at least 60% to minimize bias. Meta-analysis and systematic reviews synthesize evidence across multiple studies. Meta-analysis statistically combines results from multiple studies to estimate overall effect sizes. It provides the highest level of evidence by pooling data from many sources. Individual studies are combined through meta-analysis to produce a more precise overall estimate. Forest plots visualize individual study effects and the combined meta-analytic estimate. The meta-analytic effect size is a weighted average, where each study is weighted by its precision. Weights are typically the inverse of squared standard error, so more precise studies get more weight. We assess heterogeneity to determine if study results are consistent or variable. I-squared statistic quantifies heterogeneity as percentage of variance due to true differences versus chance. By convention, I-squared of 25% indicates low heterogeneity, 50% moderate, and 75% high. Reliability and validity are fundamental concepts ensuring research quality. Reliability refers to the consistency and repeatability of measurements. Validity asks whether we're actually measuring what we intend to measure. Valid measurements cluster tightly around the true value, like arrows hitting the bullseye. Reliable but invalid measurements cluster together but miss the target, like consistent bias. Cronbach's alpha measures internal consistency of multi-item scales. Alpha equals k over k minus 1 times 1 minus the sum of item variances over total variance. By convention, alpha greater than 0.70 indicates acceptable internal consistency. Here's an important question. Can we have reliability without validity? Yes, we can, but it's not useful, like a broken clock that's consistently wrong. Ethical considerations are paramount in all research methodologies. Core ethical principles include respect for persons, beneficence, and justice. These three pillars ensure research protects participants while advancing knowledge fairly. Informed consent requires that participation is voluntary, informed, and given by competent individuals. The risk-benefit ratio must be favorable, with benefits outweighing potential harms. Mathematically, we want benefits divided by risks to be greater than 1. Vulnerable populations like children or prisoners require extra protections. Data privacy demands proper anonymization and secure storage of participant information. Selecting the appropriate methodology depends on several key factors. Consider your research question, available resources, and practical feasibility. The research question drives method selection, which determines specific design choices. Exploratory questions about new phenomena call for qualitative methods to understand complexity. Hypothesis testing with predictions requires quantitative methods for statistical inference. Making causal claims requires experimental or strong quasi-experimental designs to rule out confounds. Think of methodologies as tools in a toolbox. You choose the right tool for the job. No single method is universally best. Each has strengths and limitations for different purposes. Let's work through a complete practical example to tie everything together. Suppose our research question is, does regular exercise improve academic performance in students? Step 1. We choose experimental design to establish causality. We randomly assign students to exercise intervention or control group. Step 2. Calculate required sample size for adequate power. For example, if the expected effect size is 0.5, we need approximately 64 participants per group, so 128 total participants. Remember to always consider the ethical implications of your research and ensure the validity of your methods.